Today, I have to deliver a lecture on molecularity and order of reaction. Actually, these two terms are used in chapter chemical kinetics. You must be aware about chemical kinetics. It is a branch of science that deals with the rate of reaction. The factors that affect the rate of reaction, like concentration of reactants, like temperature, pressure, your catalyst, and what is the what is the mechanism of a reaction? If a reaction takes place, suppose there are two types of reaction. One is elementary, the other is complex reaction. Elementary reaction is one state reaction. Complex reaction is more than two or more than two state reaction. So this is when the chemical reaction takes place in two or more than two steps, in a sequence of two or more than two steps. It is known as reaction mechanism. So with the help of in the study of chemical kinetics, we are basically concerned with the mechanism of reaction. What is the mechanism of the reaction? We'll discuss this also, how the mechanism is decided early, what are the parameters that is used to understand the mechanism of the reaction. But here my topic is focused on molecularity and order of reaction. Actually, chemical reactions are classified on the basis of molecularity and order. Reactions are called unimolecular reactions if the molecularity is one, bimolecular reaction when molecularity is two, molecular reaction when molecularity is three. In the same way, reaction is called zero order reaction when order is zero, first order reaction when order is one, second order reaction when order is two. So we have to discuss molecularity and order of reaction. Okay? But today, in this video, my lecture will be focused, limited to molecularity of the reaction only. Molecularity. Molecularity. Actually, in order to define what is molecularity, we, we have to see there are two types of reactions. Chemical reactions are of two types. Chemical reactions. One is, first type is elementary reaction. Elementary reaction. And another type is complex reaction. It is a complex reaction. Reaction is single step reaction. Single step reaction. That is the reaction taking, taking part, taking place in one state. And a complex reaction is one that takes part, that occurs in the sequence of sequence of two or more states, two or more states called the reaction mechanism. Called the reaction mechanism. So a complex reaction has a reaction mechanism. Now, molecularity of, of an elementary reaction. Elementary reaction. Now, consider any reaction, a reaction like your 2HI, dissociation of HI into hydrogen and iodine. This this reaction is an elementary reaction. It takes place in single step, in one and one only one step, as indicated by this chemical equation. Now, You know that a chemical reaction involves breaking of bonds in the reactant molecules and making a bond in the product molecules. If this reaction to occur, the bond between H and I has to be broken, and then bond between two HI atoms will form, and bond between two iodine atoms will form. So a chemical reaction is nothing, but it is redistribution of bonds. The breaking of bonds and making of bonds. Now, breaking energy, it is endothermic process, whereas breaking of bonds, whereas making of bonds is what? It is exothermic. It is accompanied by release of energy. Whenever a bond is formed, energy is released. So formation of bond is not a problem. Here, energy is evolved. But the problem lies in the breaking of bonds because energy is needed. Now the question arises from where energy comes. How does reaction molecule receive its energy for breaking the bond? Actually, reactant molecule receive energy for breaking the bond by collision between themselves. That is, in this reaction, the energy is acquired by collision between them. Now, when two HI molecules collide, one molecule during collision, there, there will be redistribution of energy. One molecule will transfer energy to the other molecule. The energy of one of them will increase, and that molecule will become energy rich molecule and will have sufficient energy to break its bond. But when two molecules collide, when two reactant molecules collide, they do not they do not convert directly into product, but first they collide to form transition state of the reaction. Transition state is a state between in the reaction path between reactants and product, in which bond breaking and bond making are taking place simultaneously. The energy involved in the making of bonds are utilized in breaking the bonds. Just say where this is one HI molecule, and this is another HI molecule. They collide to form this H H I I this. See here the this HI bond. See this dotted line. This is this shows that the bond is undergoing breaking. This bond is getting this bond. This is full bond. That's full line means bond is a strong. Bond is very strong. They are H and I are strongly bonded. But here H and I atoms are loosely bonded. The bond has become weak due to collision. Yeah, also this HI bond. There are two molecules. This one has become weaker. This bond has also become weaker. And at the same time, this means these two bonds are getting broken. And the bond between two HI atoms, this, and bond in iodine molecule, two iodine atoms are under formation, are getting formed. So here, bond formation and bond breaking, both are taking place simultaneously, transition state. The energy involved in the formation of this bond is utilized in breaking this bond. The energy released here is utilized in breaking of this bond. So the bond formation, which is accompanied by energy, that energy is utilized in breaking the bonds. So this is the transition state of reaction. This state is most unstable. It has the highest energy in the reaction path in between reactant and product. When we go from reactant to product in the reaction, which is called reaction path, in the reaction path, this occupy the point of highest energy. And the energy the highest it means it is most unstable. It has only transient existence, transient, transient existence. That is, as soon as it is formed, it gets broken. Okay. So formation and breaking of this transition state take place almost simultaneously. Now, transient existence is because of very high energy of this. This energy is actually vibrational energy of the molecule, and because of very high vibrational energy, the vibration is very strong, and as a result of vibration, the molecule breaks, breaks into pieces, that is, breaks into product. So this converts into product. H, H plus I. Now, this transition state, as I might have told, this is suppose this is a reaction path, reaction coordinate, reaction coordinate, and this is your the enthalpy of the reaction. Enthalpy is a type of energy possessed by every substance, and it is that form of energy that is converted into heat, or heat is converted into enthalpy. So enthalpy is also called heat content. It is denoted by the symbol H. Now suppose this is the energy of what? This is the energy of the reactant. This is the reactant, that is the child reactant. And this is the energy of the product. We are actually considering the exothermic reaction. The energy of product is enthalpy of product is less than the enthalpy of reactant. So there will be decrease in enthalpy during the reaction. And decrease in enthalpy means evolution of heat. Now, when reactant molecule collide together, then their energy increases like this. And finally, it attains some energy. And after retaining that energy, it again bond formation begins, and therefore energy is, is decreased. The product is formed. Now, transition state lies here. Transition state lies here at the peak of the energy diagram. It has the highest energy in the reaction path. The energy between the enthalpy here, the enthalpy of reactant is HR, and here the enthalpy of product is HP. So this is delta H of the reaction. This is delta H of the reaction, and this is equal to HP minus HR, and this is negative. That is reaction is exothermic. This is exothermic reaction. Okay, so what I mean to say is that this transition state has one transient existence. It occupies the highest energy point in the reaction path between reactant and product, and it soon converts into product, or it may either transition state will slide down in this direction, or it may also slide down in this direction. So this means transition state formation is a reversible process. This. So we have to conclude now that the chemical reaction takes place by collision between the reactant molecules. The collision first forms transition state, and then transition state converts into the product. Now, the number of reactant molecules, the minimum number of reactant molecules that is required to collide together to form of the reaction. Transition state of the reaction is known as molecularity of an elementary reaction. The molecularity of an elementary reaction is the number of the minimum number, minimum number, the minimum number of, molecules, atoms, or ions of the reactant that is that is required to collide, required to collide so as to form transition state of the reaction of the reaction reaction is called molecularity of the reaction. Reaction. One point here I want to have here. The transition state is purely a hypothetical state. It has not real existence. But it is supposed to possess all the properties which a normal molecule possesses. For example, a normal molecule possesses internal energy, enthalpy, energy, work function, entropy. In the same way, this transition state also possesses all these properties, although it is purely hypothetical. Okay, this is the molecularity of this reaction. Therefore, the molecularity of this. So molecularity of this reaction 2HI, this is S2 plus I2. Molecularity is molecularity of this reaction is 2. That is, it is known as a bimolecular reaction. Bimolecular reaction. Okay. It is called bimolecular reaction. The molecularity of this reaction is 2. It is an elementary reaction. Now we have to see what is molecularity, a complex reaction. Molecularity of a complex reaction. The molecularity of a complex reaction. Complex reaction. Let us consider the reaction 2NO plus 2H2 N2 plus 2H2 N2 plus 2H2. All the reactants and all the products are in the gaseous state. This is gas phase reaction. NO is the gas, hydrogen is also gas, nitrogen is also a gas. And since this reaction is carried out at high temperature, so this water is also in the form of vapor in steam, and it is also gaseous in nature. Now, this reaction you see, actually, the rate expression of this reaction, the rate expression The rate expression is also called rate law of the reaction. Rate law is like this. The rate of formation of nitrogen dN2 by dt, dN2 by dt, dN2 is the small change in the concentration of nitrogen divided by dt is the time taken for this change. So dN2 by dt is the change in concentration of nitrogen per unit time. And change in the current means increase. The change is positive, that is increase. The increase in the concentration of nitrogen per unit time. So this is the rate of reaction. At what rate nitrogen is being produced. Now it has been found experimentally that when the concentration of nitric oxide is doubled, when the concentration of nitric oxide is doubled, the rate of formation of nitrogen increases fourfold. Once again, I am repeating, it has been found experimentally that when the concentration of oxide is doubled, keeping the concentration of hydrogen constant, the rate increases 4 times. This means the rate of formation of nitrogen is proportional to concentration, square bracket means molar concentration, concentration of NO2. That is when this is what? When this is doubled, then the rate will increase 2 power to 4. The rate will increase 4 times. When concentration of hydrogen is constant. And when concentration of nitric oxide is constant, then it is found that the rate when the concentration of hydrogen is doubled, keeping the concentration of nitric oxide constant, then rate is just doubled. This means the rate of reaction is directly proportional to the concentration of hydrogen, that is proportional to the first power of the concentration of the reactant. Okay, so here, and when the concentration of both NO and hydrogen are doubled simultaneously, the rate increases 8 times. This has been experimentally, and therefore, this experimental observation is expressed in the following mathematical form. This is expressed in the following mathematical form. Okay, this is known as rate law of the reaction. Now, this rate law of the reaction, which is experimentally based, is not at all consistent with this chemical equation. Because according to law of cross-section, whenever, according to law of cross-section, the rate of a chemical reaction varies as the product of the active mass means molar concentration, the molar concentrations of the reacting species, So since here there are two molecules of NO plus NO, and two hydrogen, N2 plus 2H2. So according to law of cross-section, according to law of mass section, the rate of this reaction should be plus dN2 by dt should be proportional to concentration of NO into concentration of NO into concentration of hydrogen into concentration of hydrogen. That is, this is concentration of NO power 2 into concentration of hydrogen power 2. This should be the rate law of this equation reaction, according to law of position. But they experimentally verified it like this. This means, this does not mean that law of perception fails in this case. Because law of perception cannot fail. Law of perception is based on thermodynamics. And laws of thermodynamics can't fail so long as this universe exists. So then why there is a difference? The difference means this chemical reaction is not an elementary reaction. It is not an elementary reaction. It is a complex reaction. And law of perception applies only for the elementary reaction. So if the rate law as expected from law of perception is not observed experimentally, the experimental rate law appears to be different from that expected from law of perception. It immediately suggests that the reaction under consideration is not a elementary reaction, but it is a complex reaction. So it is a complex reaction. Now we have to give the mechanism for this reaction. Now we will discuss this in another lecture, that how the mechanism is suggested on the basis of what? On the basis of the heat law. We will discuss it in another lecture. Here, this reaction, it is a complex reaction, complex reaction, and, and it is a complex reaction, and it occurs in the sequence of in the sequence of following following three steps, following three steps. First step is NO plus NO. That is two molecules of NO combined to form N2O. This reaction is reversible. And this reaction is very fast reaction. On what basis do we say this reaction is very fast? This reaction is very fast because we have observed this in the lab. This reaction is very fast. Or we can also base this on the basis of our conception. Here actually, NO what? NO molecule has this structure, N double bond O. N has one unpaired electron. Another NO molecule has also one unpaired electron. Now these molecules, two molecules, they are odd electrons, unpaired electrons, get shared, and a covalent bond is formed between these two nitrogen atoms. Due to sharing of electron, these two electrons, a bond is formed. So in this reaction, we see that no bond is to be broken. Only bond is to be formed. And since only bond is to be formed, no bond is to be broken. Breaking a bond is a different task, energy needed. Here bond is only formed. So this reaction is very fast. So this reaction is fast. And this reaction is reversible also. This reaction is reversible also. Why it is reversible? Actually, when two NO molecules combine to form N2O2, a bond between two nitrogen atoms, that is NO, a bond between N and N is formed, and due to formation of bond, energy is released. A release of energy means decrease in enthalpy. So this forward reaction is accompanied by decrease in enthalpy. And decrease in enthalpy is a condition of spontaneity of the reaction. If delta is needed along this reaction, along backward reaction, delta H will be positive. Then why this reaction takes place? This reaction takes place because in this state, Delta S, the change in entropy is positive. That there is the increase in entropy of the system. Why entropy increases? Because from one molecule, when they go to breaks, two molecules of NO are formed. There is increasing population particle, and when there is increase in the population, there is increase in randomness of the system. There is increase in the disorderness of the system, and you know that entropy is the leader of degree of order or degree of disorderness or the randomness of the system. So entropy increases in the backward reaction. This delta S positive is also the condition of responsibility. So this means the forward reaction is driven by enthalpy, the backward reaction is driven by entropy. Now, second, this N2 molecule, N2 molecule, N2O2, this reacts with one molecule of hydrogen, collides with one molecule of hydrogen, form N2O plus H2O. This reaction is a slow reaction. Why this reaction is slow? Because here this molecule has this structure N double bond O, double bond O. Now, when hydrogen combines with oxygen to form H2O, this bond has to be broken. And this is the double bond. In order to break double bond, more energy is needed. The breaking of double bond is required as compared to the breaking of single bond. So here the bond breaking is difficult. So this process becomes slow. And third one is N2O plus H2O. This is N2 plus H2O. This step is also very fast step. This step is also very why this is fast? This is fast because N2O has this kind of a structure, N triple bond N, coordinate bond O. N is positive because N is electron pair donor and O is negative. This this when this is coordinate bond, very weak bond. So hydrogen very easily remove this oxygen from that nitrogen. And this becomes more easier because the more electronegative nitrogen which is more electronegative, is positively charged. This is sign of what? Instability. The system is very unstable, and therefore this bond breaking takes place immediately. This now these three states all are elementary states. And you know that every elementary reaction is accompanied by formation of transition state in the reaction path between product and reactant. So here is the transition state formation, here also transition state formation, here also transition state formation. In the transition state formation of this reaction, two molecules of NO collision is needed. So molecularity is 2. Here also molecularity is 2. Here also molecularity is 2. Now the question arises, what is the molecularity of this overall reaction? The molecularity of this overall reaction, actually, this is the slowest step out of these three steps. This is the slowest step. And slowest step is called the rate determining step, RDS, rate determining step. Why? Because unless N2O is formed, N2 can't form because hydrogen will have to wait because formation of N2O is very slow. So hydrogen will have to wait for the formation of H2O. So the formation of nitrogen will be delayed. The rate of formation of N2O and will be equal to the rate of formation of nitrogen. And therefore, we see that the formation of nitrogen occurs at the same rate as if N2O is formed. So this is called rate determining state. And the molecularity of the rate determining state. Here the molecularity is 2. This is known as the molecularity of the overall reaction. the molecularity of the complex reaction. That is the number of molecules, the number of molecules, atoms, or ions of the reactant and and or intermediate coming into contact coming into contact and colliding simultaneously and colliding simultaneously in the Slate state, that is rate determining state, is called molecularity of the complex reaction. The number of molecule atoms or ions of reactants and or intermediate coming into contact and colliding simultaneously in the specific, the related in the state of the mechanism. Here, write, please, here, write down of the mechanism is called molecularity of the complex reaction. Therefore, what will be molecularity of this reaction? The molecularity of this reaction will be equal to the molecularity of a state, molecularity of state 2, that is this last state. And this is equal to how much? Last state. And this is equal to 1 plus 1. One molecule of N2O2 and one molecule of hydrogen. 1 plus 1, that is 2. This is the so this is a bimolecular reaction. The mechanism is called bimolecular, where the molecularity of Suez state is 2, that is Suez state is bimolecular, then we say that the mechanism is bimolecular. This is all about the molecularity of the reaction. Understood? Am I?